Hello, hey, we're going to look at problem 5.5 for numerical methods. This has been, some people have asked for an example of this, and I think this is just a good baseline to start from. I'm going to start with a cleared screen, and I'm working here in this directory. So we're going to create a new file. So we're supposed to create a function that does this, but here's the way I'm going to do this. I'm going to do bisect. I'll just call it bisect. I'm going to create it. Yes, create it. Okay. So the way I usually work when I'm creating functions is the first thing I'm going to do is I'm going to kind of get it to work without it being a function. Then I will functionalize it. So eventually it's going to be function x is equal to bisect, and then there's input, and we'll get into that. But right now I'm going to comment that out, and I'm just going to do this stuff by hand. So here's a problem f. So f is equal to at x minus 12 minus 21 times x plus 18 times x squared minus 2.75 times x cubed. So now the basic bisection method is what? You cut it in half, you split the difference, and figure out where it is. So I'm going to first do it as a for loop. For I is equal to 1 to 1,000. I'm arbitrarily doing a whole bunch of steps, okay? And what I want to do is I want to create my middle point, xm, and it's equal to xu minus xl divided by 2. So halfway in between xu and xl. So we need to define xl and xu. So xu is going to equal, and I'm going to come over here and it says, hey, let's use the xu of 0 and xl of minus 1. So fair enough. The upper is 0 and xl is equal to minus 1. So I'm going to come in here, I'm going to do that. And then my basic question is the function evaluated at the middle times the function evaluated at one end positive or negative? So it doesn't matter which end you do. So I'm going to arbitrarily pick the left side. So if function at x lower times function at x middle, if that is less than 0, so that would mean that the function, that would mean that it crosses the answer on the left side. So if it crosses on the left side, therefore xu is equal to xm. Otherwise, xl is equal to xm. Boom. And that is the function on its simplest level. So let's, just for giggles, let's kick this out. So we're going to come in here and we're going to do this first part that I just kind of glossed over. We're going to do it graphically. So let's go through and we're going to say f plot. I hate f plot, but I'll do it anyways. F, and since they gave us an answer, it's either going to be between minus 1 and 0. I'll do between minus 1 and 0. Okay, so let's run that and see what we get. Okay, so, and here's, I'm going to turn my grid on, zoom on, hold on, box on. In the future, that will just be called GZHB, but we'll call that. Okay. And I'm going to clear everything, so I'm starting fresh every single time. Okay, what warning is it? It's giving me a warning of something. Oh, it's getting upset that I wrote this function without the dot operator. So if I put a dot operator there and a dot operator there, when it's calling fplot, it wants to be able to call it more efficiently. And so there, the warning goes away. Okay, so there we go. So let's zoom in. So we're looking at where it crosses 0, so here. So the answer needs to be around, what, minus 0.415-ish, okay? And so let's see what we get. XM is that. So that I do not believe. So let's go through and figure this out. I actually am purposely, not purposely making mistakes, but I'm purposely doing this on the fly so you can kind of see the debugging process as well. So we're going to come in here, and so xm is halfway between the upper and the lower. xu minus xl divided by 2. Oh, well, there's the problem. That needs to be plus xl. Okay, let's try that. And there we go. We have the right answer, right? So there is our answer of minus 0.416. Turns out the average of the two, you have to add them, not subtract them. Who knew? Okay, so there we go. So that is the basic, simplest option to do this. Okay, now we're going to start making it, we're going to kind of polish it up, make it the way that we're supposed to do it. So one of the things we're doing 1,000 steps. Well, how many steps do we really need to take? Well, the whole point is we need to keep on going, keep on doing the next iteration until it's not really gaining us anything anymore, right? And so how do we know when it's not gaining us anything? Well, when our difference from our current guess and our last guess starts to be so small that it doesn't matter, then we can stop. So how do we do that? Well, that is what we call ES and EA. So we've gone through in the past and we've defined, say, ES as 0.5 times 10 to the sig figs, and that's to the minus sig figs. You'll notice I do not do 2 because I'm not going to multiply the answer by 2 to get it to percent. So there is our ES, okay? And so we need to go through, and now what are we doing? Instead of this for statement, we're going to do a while our answer, or error, and we're going to call it EA, is greater than ES. So that is basically what we're saying. And what is EA? EA is a measure of how much does it change every time. And I'm going to do the absolute value of EA. So while the absolute value of EA is greater than ES, do this process. Okay. So now again, first pass, last pass. The first time through this thing, this EA doesn't exist. So I am going to just set it to something. I use 999. It helps catch things in case there's, you can see that and recognize that number later if there's a problem. Okay. So now, there we go. It's going to come in here and it's going to say EA is 999 while EA is greater than ES. So ES is going to be, I didn't put num sig fig, so let's say sig fig is equal to 0.01 is what it says 1% in the book, so 0.01. Okay, so, and it's not 1. Goofy thing. Let's try this again. We're going to do sig figs of, say, 5. So 1%. So over here in the problem statement, it's where it asks for 1%. That would be ES's 0.01. But we're gonna mix it up a little bit. We're gonna do sig figs of 5. So therefore, there's our answer. Okay. So it's gonna come in here, and it's gonna come through here, and it's gonna say while absolute EA, well, EA is 999 is greater than ES. ES is this number, so therefore that will be true. It's gonna create this. But the problem is I need to reevaluate what EA is every time through. So EA is what? What is it? It's a measure of how much did it change. And so EA on the simplest level is old minus new divided by new. Okay? And in parentheses. Oops. That is what EA is. Okay, again, the new is how you kind of normalize it so it doesn't, because again, an answer of 0.1, who knows, is that a good answer or not? Depends on the range that you're working with, right? But once you do that, you're getting a fractional or a percent error, and so that's all good. So what is the old, what is the new? Well, the new is this. We just calculated it. So what is the old? So the way I'm going to do this, I'm going to say old is equal to XM. I'm going to grab it before it gets changed. It's going to update it right here, and then it's going to keep going about its merry way. So the only problem with that is first pass through here, what is XM? Well, it doesn't exist. So again, I'm going to come in here and say XM is equal to 999. I don't know. Just doesn't matter. I just want to make sure it doesn't. The only problem is if I go through and say XM is equal to XU plus XL divided by 2. Although that is true, the first time through here, EA is going to be 0 because this is going to be that, and then it's going to turn around and recalculate that same thing, and so that's going to be a problem. So I don't know, XU, 4, whatever, just come up with a number so that this doesn't get tripped up the first time through. And now this should work. Now for giggle, I'm going to do something unnecessary. I'm going to say n is equal to n plus 1, and I'm going to say up here n is equal to 0. The only reason I'm doing this is I want to see how many times does it take to iterate. Okay, so I'm going to run this. And it got to 7 for me because of new, because I forgot new is really XM. So I could rename it, but that just seems unnecessary. So there we go. So it took 19 iterations to get that answer, and there you go. So that is how you do that. So that is how the code works. But now we need to make it a function. Okay. So, and specifically in the function, it asks for well, let's look here. This function asks for to pass the function handle, the lower, the upper, and the ES, and the max iterations. I'm not going to pass the max iterations. if you're doing it this way, you do not do a max iteration. So let's create a new file, and this is going to be the homework. And so we're going to say we're going to make this the function. And what do we want to pass out? We want to pass out where it occurs, this xm. Now, when we're doing this as a function, all of a sudden, we do not want to have that stuff kick out to the screen. It'll confuse the issue. Okay, I'm going to copy most of this stuff. Well, no, I'm not. So what comes in, the function, the xl, xu, and I'm going to go ahead and just pass it es. And that's what I'm going to say that I want to pass to the function. So I'm going to come in here, grab a lot of this stuff, and then I'll figure out what I need to have in which place. Put this over here. So there's my function. Over here is where I'm going to clear it. Es is that. I'm going to create the fplot xu, xl. This ea, xm, and n I don't need. And so I want to say x is equal to bisect of f, comma, xl, comma, xu, comma, es. And I'm going to come over here. So this I definitely need to delete. This I need to delete. Sorry. This definitely. This. The XL, XU, EA. Now this I need to leave in here, right? Because this is part of, and I want to get rid of that. I want to leave this in here because that's part of how it calculates this. And oops, I got rid of EA is equal to 999. So now you'll notice I can't run this. If I do this, it says no, you can't do it because it's a function, which is why I developed it the first time. I make sure I save the function, I come over here, and then I try to run it. Okay, and it got upset with me, output x. Okay, so fair enough. It's getting upset that I'm saying x is the output, but I never calculate x, and instead here I call it xm. So again, save it here, come over here, run this, and I get my answer of that. So that's the deal. So this is now the function, fairly clean. You're passing it the function, the lower, the upper, and the es. Now, if you wanted to pass it, say n, that's not it's a sig figs, then that's totally reasonable. Then you can come in here and say es is equal to 0.5, 5 times 10 to the minus sig figs. Totally reasonable, totally acceptable. Just kind of a style issue. I kind of like to do more of the stuff outside of the function. It gives me more flexibility inside the function. So I personally am not going to do that. If you do that, that's fine. You'll get a good answer. Instead, I'm just going to pass it es. So that the reason I would do that, okay, so this is saved. I'm going to come over here. I can calculate es this way, or I can say, you know what, never mind. Let's just do es is equal to 0.01. I think that's actually what it asked for in this problem. Run that, and I'm going to get the answer. Whereas if I did the sig figs in here, that's the only way I can do it. I can only send it the sig figs here. I can use the sig figs to calculate es, or I can just make up a number. Either way is fine. But so there you go. That is how I would do the bisection method. Pretty straightforward. The only thing really kind of extra in this is this old statement. You could actually probably integrate this into here, doing this math in here. At a certain point, it becomes, you're trying to get squeeze water from a stone. Eventually you're doing unnecessary extra effort just to get it just a little bit better. Now, if you were going through and doing this and it had to do 10 million times, then maybe it'd be worth it. But quite frankly, you would not use the bisection method if that's what you were doing. But anyways, so there you go.